everybody, this is the third video on limits review for the summer videos. In this video I'm going to be talking about finding limits algebraically and the three main methods of doing so. In this video I'm going to be talking about direct substitution and dividing out. In the next video I'll talk about one-sided limits, especially when they go to infinity or negative infinity. The first way of finding a limit algebraically is the quickest way, and it involves the least work. It's direct substitution. Whenever you have a function like 2x squared minus 3x, and you're trying to find the limit as you approach a certain x value, so in this case negative 4, you should always try direct substitution. And all that involves is taking the x value that you're approaching and plugging it in to the function and seeing what y value you approach. So in this case, all I need to do is rewrite it with the x value I'm approaching, plugging it in, and in this case, 32 plus 12, I get a number. There was no issues, so you know that the limit as x approaches negative 4 of your function was equal to 44. That is your y value. And the reason it worked out so nicely is that this is a quadratic, so a parabola. It's a continuous function, and continuous functions you can usually just use direct substitution. Let's say you try direct substitution and it doesn't work. One of the reasons that it might not work is if you get 0 divided by 0, which as we know is undefined. So in this case, we are going to call 0 over 0 the indeterminate form. That's what it's usually called in calculus. If you get 0 over 0, that means that there is a hole in the graph. I'll be drawing what it looks like in a second so you can see why this would happen. If there's a hole in the graph, what you're going to need to do is factor and cancel out the common factor. So if you get 0 over 0, that means the numerator and the denominator share a common factor, and you need to cancel it out. Once you do that, you should try direct substitution again because you shouldn't get 0 over 0 anymore. Let's take a look at this example here. X is approaching 2, and I have the function 2x squared minus 3x minus 2 divided by x minus 2. I'm going to try direct substitution first. So I'm going to do 2 times 2 squared minus 3 times 2 minus 2 all over 2 times 2. Don't get in the habit of just saying, oh look, there's 0 in the denominator, there must be a hole. Because there's only a hole in the function if you get 0 over 0. If you get a number over 0, that doesn't mean there's a hole. That means there's a vertical asymptote instead. But if you do the math out, you see that you will get 0 over 0 in this case, so we're going to need to factor. So let's continue it on this page here. So I'm going to factor the numerator and the denominator. We're going to need to use guess and check in the numerator. So let me try 2x and x here. And let's see, we'll try plus 1 and minus 2. This is going to work here. As you can see, I have x minus 2 in the numerator and the denominator. So what I have next is the limit as x approaches 2 of 2x plus 1. So really, I'm just left with a line after I cancel the common factor. Let me try direct substitution again. And no issues, I get 5. So basically what happened here is, because the common factor x minus 2 canceled, that means there is a hole in the graph at 2. Now whenever I plugged 2 back into the simplified form, I got a limit of 5. So that means as I approach 2, my y value intends to go to 5, but it doesn't actually get to 5 because of the hole in the function. To get the rest of the graph, I'm just going to graph 2x plus 1. That's a line with a y-intercept 1, up 2 over 1, up 2 over 1, up 2 over 1, and here we go. That's what it looks like. Let me try this next example here. This one's going to look a little bit different whenever we graph it. So I have a rational function, because there's an x in the denominator and the numerator. If I try plugging negative 1 in using direct substitution, minus 3, I am in fact going to get 0 over 0. That means there's a hole in the graph. So I'm going to factor quick and get rid of the problem here. So I have the limit as x approaches negative 1. So I have a difference of 2 squares in the numerator. And I have x. Let me do minus 3 plus 1. And here we go. Here's the common factor. X plus 1 cancels out. That means there's a hole in the graph when x equals 1. We'll draw that in a second here. What I am left with now is the limit as x approaches negative 1 of x minus 1 over x minus 3. That's my simplified rational function. Notice this one's different because I'm left with a rational function still. This function will still have asymptotes, whereas this one here was just a line, no asymptotes. Let's see if direct substitution will work now. I have negative 1 minus 1 over negative 1 minus 3. Negative 1 minus 1 is negative 2 over negative 4, so 1/2. It works. So the limit is 1/2. The y value is going to get very close to 1/2 as x gets very close to negative 1. So I have negative 1. Let me put a couple tick marks here. Alright, so at negative 1, I had a limit of 1/2. Now, if I'm going to graph the rest of this thing, I have a vertical asymptote at x equals 3. And I have a horizontal asymptote because the degree is the same in the numerator and the denominator. I have 1 over 1. So I have a horizontal asymptote of 1. Oops. And let me see here. We can also graph the x-intercept and y-intercept. So for the x-intercept, I'm going to set my numerator equal to 0, and I get 1. And the y-intercept, I'm going to put a 0 in for every x. I have negative 1 over negative 3, so 1/3. So here's my x-intercept, and here's my y-intercept. So my graph will look like this. And here, let me just get one more point whenever x is 4. If I plug 4 into my simplified function, I'm going to have 4 minus 1 over 4 minus 3. That'll give me 3 over 1. So 3, 1, 2, 3. So I can just pretty much assume that my graph will look like this and approach the horizontal asymptote and shoot up at the vertical asymptote. So there are several examples like these in your summer work packet, so hopefully these help out with those.